Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On, and in this tutorial video we'll go through the 16 to 18 years old Cambridge International A-Level paper. This is one of the earlier papers. When I say earlier, I mean from the previous syllabus. So some of the questions we deemed might no longer be relevant to the current syllabus for your current exam. So always check your specification, yeah? This is June 15, paper 1-2. So paper 1, variant 2 for the different regions, different set of questions, but still covering pretty much the same learning objective as what the syllabus intends for this 16 to 18 years old A-level curriculum. In this first question, even though they had talked about the use of data booklet, which is relevant, we know that the data booklet is being phased out from being a separate booklet into being embedded within the question paper itself as per the new 2022 syllabus onwards. Anyway, so we're looking at the same electronic configuration and also the same number of neutrons. So really we are not looking at sizes, we're looking at the periodic table. So we know that in the periodic table, nitrogen, oxygen, fluorine are consecutive elements in group 15, 16, and 17 with 5, 6, and 7 valence electrons respectively. So here we got 15, nitrogen is element 7, and then oxygen is element number 8, fluorine is element number 9. These are negative, these are 2 minus, these are 3 minus. In terms of the protons, 7, 8, 9. In terms of the electrons, we know that this has gained 3 electrons, this has gained 2 electrons, this has gained 1 electron, and therefore this is 10, 10, and 10. These are what you call isoelectronic. They have the same total number of electrons, therefore they will have the same electronic configuration by extension of that concept. Same number of neutrons. We know that number of neutrons is to do with the nucleon number, which is the number of the protons and the neutrons in the nucleus of an atom. And you have the smaller number at the bottom, which represents the atomic or the proton number. So 15 minus 7, you're going to get 8 neutron there. 16 minus 8, you're going to get neutrons for the oxygen 16. And 19 minus 9, you're going to get 10 neutrons for this fluorine 19. And obviously these are not the same number of neutrons. I can tell you A is not correct there. In terms of neon, I have 10 protons, fluorine has 9 protons, oxygen has 8 protons, but be careful, this is oxygen 18, so 18 minus 8 is 10 neutron, 19 minus 9 is 10 neutron, 20 minus 10 is 10 neutron as well. And then in terms of neons, element number 10 has 10 electrons. So this one has 10 electrons, which is the same number of electrons as O2 minus, because the number of neutrons, even though there is more neutrons in oxygen 18 than oxygen 16, that does not affect the number of electrons whatsoever. So 10, 10, and 10, including that for neon. Fully fill out the shell, same electronic configuration as a noble gas there. B is our answer because it satisfies not only the first condition, but the second condition, number of neutrons there. Question number 2, we have a shell of a chicken egg which made up the 5% of the mass of an average egg. So 5% of 50 grams, which is the mass of one average egg. So N there refers to 1. So how much of the shell is actually pure calcium carbonate? So how much of the shell is actually pure calcium carbonate? So the shell, which is just calcium carbonate, is going to be 5 out of 100 because percentage is out of 100% times 50 grams. So 5 divided by 100 times 50, you get 2.5 grams. Now the next question really is, I need a balanced equation because the calcium carbonate will react with ethanoic acid. So this is quite a tricky one because ethanoic acid is a carboxylic acid, so CH3CO2H. If I draw the skeletal formula, you would know, but then you might not have learned the organic chemistry bit yet. So I'm going to draw the simple carboxylic acid form in the display form like that. So that thing is going to give me a salt. The salt I'm going to get is Ca2+. The salt I'm going to get from the acid is called ethanoate. After I lost the H+, I have a negative charge. I have a negative 1 charge on the ethanoate. Plus 2, minus 1, you know better about the exchange of valency. You're going to need 2 of these anions in order to balance the charge of these cation. And therefore, you're going to get calcium, ethanoate, 1 calcium, and 2 of these ethanoate to balance the equation. And you're going to get water as well because this is neutralization. So you're going to get water. But then importantly is that you need 2 of these ethanoic acid because you can have 2 of the carboxylate or the 2 of the ethanoate. And you have 2 of these hydrogen, 2 hydrogen, and 1 oxygen from the CO3 2-, such that now you're left with CO2 gas. So this reaction between metal carbonate and acid, metal salt, water, and also carbon dioxide gas. So you have information on this neutralization of ethanoic acid. So we have information on ethanoic acid. We want to know how much of calcium carbonate actually reacts. So I need the mass of calcium carbonate, and since I'm working with reacting masses, I should really work out the MR of calcium carbonate from the periodic table. So 40.1, this is the AR, relative atomic mass of calcium from the periodic table, plus 12.0 plus 16.0 times 3. So I get 140.1. So what I have there is setting up my mole ratio. So the mole of the acid is to the mole of the carbonate. From the balance equation, 2 mole of the acid reacts with 1 mole of the calcium carbonate. So on top there I have not the mass, hang on, I want the mass of the calcium carbonate, so by right I should have the mole of the calcium carbonate on top. Actually it doesn't matter, but I just find it easier for me to rearrange the equation that way. From the balance equations, 1 mole of carbonate reacts with 2 mole of the acid. Balance equation, very, very essential there. So on the top there, I have the mass of the calcium carbonate divided by the MR, which is 140.1. And what I have at the bottom, I have N equal to CV because these are solution chemistry. So 50 times 10 to the minus 3 times 2.0. Rearrange your equations. Do not move the half on the other side. Keep them there because you're just moving the number on the right hand side to the left hand side. So the left hand side still have half there. So 50 times 10 to the minus 3 times 2.0 would have gone there. And then I have the 140.1 at the bottom here, which I will move up and become multiplication. So it become multiplied by 140.1. Press it onto the calculator. And what do I get? And I get 7.005 gram. This is the total mass of calcium carbonate required, and this is the mass of calcium carbonate from the shell in one egg. This is per egg. So how many eggs do you need in order to get 7 gram? Therefore, 7.005 gram divided by 2.5. I wonder if I have done the right thing. So 40.1 plus 12.0 plus 16.0 times 3. You see, I've done the wrong MR of these, okay? I've done a lot of MR of calcium carbonate in my entire life, and I know when that number is a bit wrong. That looks like 100.1 instead of 140.1. So that is going to be divided by 100.1. So be very careful about this kind of thing, all right? I have a hunch about this because I've done calcium carbonate for many times my entire life, okay? So that thing is wrong there. So what it should be really is times 100.1. So let's try press a calculator again. And I don't think I would have gotten the answer right just now, so that's how I know my answer was wrong. So 5.005, so 5.005 gram divided by 2.5 gram per egg, I'm gonna get 2 eggs roughly. So 2 eggs are going to give me enough calcium carbonate to react and neutralize this much amount of the ethanoic acid based on this balance equation there. Question number 3, so we have pH3, which is phosphate. That looks pretty much just like ammonia. So we know that it's just below nitrogen. Phosphorus is in group 15. It's got 5 valence electrons. 1, 2, 3 are used for covalent bonding. Still has a lone pair. It's going to behave just like ammonia. It's going to form something called the phosphonium. Instead of the ammonium, it's going to form something like phosphonium. It uses the lone pair to form a dative covalent bond there. So that is definitely a dative covalent bond. Which solid has a simple molecular lattice? Simple molecular lattice, well, actually by right, we never ever call simple molecule having a lattice. So this one is actually quite a wrongly worded or poorly worded question. Only the giant structure can have a lattice because simple molecules do not really have a lattice. Okay, I guess why it's correct is because it's a solid. That is because solid particles are tightly packed together. I guess that is why they call it a solid lattice there, but try to avoid the term lattice when you're talking about simple covalent molecules, okay? So solid particles packed tightly together, so they're arranged in a regular order. That is probably why they use the term lattice there. But anyway, simple molecular is the same as simple covalent structure. We have calcium fluoride, Ca2+, 2 of the F minus. This is a giant ionic, so definitely not a simple molecular. Nickel is a transition metal, so from there you know it has a giant metallic structure, so you essentially have metallic bonding between the metal cations and the C of delocalized valence electron. Silicon dioxide, SiO2, is your case study on giant covalent structure. So it's got a continuous network in this giant structure where each silicon is bonded to 4 oxygens, and each oxygen is bonded to 2 silicons, and then the silicon in turn is bonded to 4 oxygen again altogether, which means 3 other oxygen like that. And sulfur is definitely our answer. There's S8, so it looks like a W like that. So, and then looks like a W like that at the back as well. So what we have is sulfur 1, 2, 3, 4, 5, 6, 7, 8. So S8 looks like crown instead of W, they call it. Okay. Question 5, we have PV equal to nRT. So this is the ideal gas equation. We're given the temperature of 60 degrees Celsius. We have to convert these to Kelvin because this temperature is in Kelvin. The N is the mole of the gas, mass over mR, mass in gram, mR in gram per mole. R is the molar gas constant from your data booklet. R is just 8.31 joule per Kelvin per mole. How much energy is needed to raise the temperature by 1 Kelvin or 1 degree Celsius for 1 mole of any gas, that is molar gas constant there. Pressure of the gas is in Pascal, volume of the gas is in meter cube. Very, very important there. So 60 plus 273 in order to convert the 60 to Kelvin there. 60 plus 273, this gives me 333 Kelvin. Next I have pressure. Pressure of 103 kilopascal is just 103,000 Pascal. Last but not least, the volume is already in meter cube, so that one is fine. I want the mass of methane, so this is mR of CH4. From your predict table, 12.0 plus 4 times 1.0, this gives you 16.0. Of course, your calculator is going to show you 16, but you know about the accuracy of the data from your predict table, appropriate number of significant figure as stated in the syllabus under calculations, topic number 1 there. So in terms of the masses, we're just rearranging the equation. So mass equal to PVMR over RT. So P equal to 103,000 Pascal times the volume 5.37 times 10 to the minus 3 times the MR 16.0 divided by the molar gas constant 8.31 divided by the temperature in Kelvin. So set up like that, and you are going home nice and happy when you can press your calculator correctly. So I get 3.19. So the mass there is 3.198 to 2 significant figure. So 1 and 2 significant figure. We look at the third one. There's definitely 3.2 gram there. Question 6, we have metaldehyde. So whatever solid this one is, you burn completely in excess oxygen, you get carbon dioxide and water. So this is an equation for the enthalpy of combustion. This is also the enthalpy change of reaction, which this reaction represents the combustion for this metaldehyde. Now, which expression will give a correct value for the enthalpy change of formation of the metaldehyde? So given this equation here, which represents combustion, what data can we have? We can have the enthalpy of formation of these particular species, which we can use enthalpy of formation to calculate the enthalpy change of reaction, which for this reaction, it represents combustion. So let this be X. So let this enthalpy of formation of metaldehyde be X. This is for forming enthalpy change when we form 1 mole of the substance from its elements in the standard states under standard conditions. The enthalpy of formation of an element in the standard state is always going to be 0. You think back on the definition, forming the elements from the elements itself, no change in enthalpy at all. What we have is also the enthalpy of formation of CO2. So this is the formation of CO2, and this is the formation of H2O. We look at the option here. All of these are combustions, and combustions. I talk about formation of CO2. But then if we look at the equation, there are a couple of identities because these are fixed stuff from this topic. If I write down the equation, carbon plus oxygen, carbon dioxide like that, solid, gas, we can see that equation represents the formation of CO2. You're forming 1 mole of the substance from its elements in their standard states under standard condition. This is also equal to the enthalpy of combustion of carbon because you are combusting, you are burning 1 mole of the substance in excess oxygen in the standard state, the elements in the standard state, everything in the standard state essentially in excess oxygen, and that's the combustion of carbon there. So essentially that is your first identity. There is actually a second identity which you can write the equations. I think I'm running out of space, but I'm just going to tell you, you should write down the equation really and convince yourself that the formation of H2O is the same as the combustion of hydrogen. So this thing is the same as the combustion of hydrogen. This thing is the same as the combustion of carbon. Now, given the enthalpy of formation, if I have the enthalpy of formation, so what do I get? The enthalpy change of reactions is going to be the sum of the enthalpy of formation of product minus the sum of the enthalpy of formation of reactants. So people always try to remember product minus reactant. That is actually wrong because without label, your formula means nothing at all and you will make a mistake. So in terms of the products, we have the combustion of carbon plus the combustion of hydrogen there because these things are on the product side, and this thing must be multiplied by 8 because this is for burning 1 mole of carbon. You're burning 8 mole of carbon to give you 8 mole of CO2. So it's 8 times the combustion of carbon. That is correct. And that is adding with 8 times the combustion of H2 because you burn 8 mole of H2 in order to get to 8 mole of H2O. So plus 8 mole, well, 8 times the enthalpy of combustion of hydrogen to give you that because this is for forming 1 mole, for burning 1 mole of hydrogen. This is burning 8 mole of hydrogen to give you 8 mole of water. And then the sum of the enthalpy of formation of products because this formation is equal to this combustion, and then minus the formation of the metaldehyde as required by the question there. So what am I talking about? So this one is, this thing here is the combustion of the metaldehyde. So I wonder if I'm doing the right stuff. Maybe I'm doing the wrong stuff. I think I'm doing the wrong stuff because let's just rearrange our equation first. Let me use a different color ink. So this is the combustion of the metaldehyde equal to combustion of carbon multiplied by 8. So there's 8 times that. And then there is plus 8 times the combustion of hydrogen. And then minus x plus 0 because I'm just forming 1 mole of the metaldehyde. Now I want to make x the subject. So I move the minus x to the other side. So all of this is still correct. And then minus the combustion of metaldehyde. So I guess I was right, that, and minus the enthalpy of combustion of metaldehyde as I move these to the other side. And I move the minus x to the left-hand side. And that will enable me to calculate or get an expression for x, which is the enthalpy change of formation of metaldehyde there. Question 7, we know the electrolysis have been taken out from the AS syllabus, especially these electrolysis to purify copper metal, and this is from your O-level, GCSE or IGCSE level chemistry. We know that at the anode, oxidation happened because of reduction at the cathode. So reduction happened at the cathode, reduction is gain of electrons. So what happened is the copper anode, which is impure, will dissolve into the solution, and what you get is you get the copper 2 plus the 2 electrons, and the copper 2 plus that dissolve away, that has already been dissolved, will go to the cathode and gain electrons and get reduced to give you the pure copper at the cathode. So essentially you get the transfer of copper from the anode to the cathode such that the mass of the cathode will increase, the mass of the anode will decrease, but all the copper 2 plus that you gain that goes to the cathode comes from the anode, and therefore your electrolyte, which is copper 2 sulfate, will not change in its color because you are not using up any of the copper 2 plus from the electrolyte. So no change in color, B and D is out. The mass of cathode will increase. Reduction happens at cathode, as I mentioned. You gain electrons for the copper 2 ion to give you the pure copper to be deposited at the cathode there. So decrease is wrong. A is the only answer there. Question 8, we have an equilibrium. So we need to think about Le Chatelier principle in terms of shifting the positions of the equilibrium. So what conditions give the greatest percentage of N2O4? You want to favor the right hand side. You want to shift the equilibrium to the right hand side and favor the forward reactions in order to give you more N2O4. If I think about the number of molecules of gases, I have 2 moles of gases on the left, and then I have 1 mole of gas on the right. This is something you will have written down as the first thing to when explaining this kind of stuff in structured questions. This is also the first kind of thing you are thinking in your head as you're doing this kind of multiple choice question. So the more molecules of gases you have, the greater is the pressure. So what happens when pressure increases? Your system tries to counteract the change. Your system is your equilibrium. It tries to oppose the change. How does it oppose the change? It will try to decrease pressure. Tries to decrease pressure. And how would it try to decrease pressure? It will shift to the side with lesser gaseous molecule, because less gaseous molecule, lower pressure. So therefore, it will shift to the right hand side, since our right hand side has lesser moles of gases. And when you shift to the right hand side, when you try to decrease pressure, shift to the side with lesser gaseous molecule, shift to the right, my N2O4 will increase. So I do want pressure increasing there to give me a higher yield of this N2O4. So now I'm left between A and B, and not C and D. Next up is to do with temperature. In terms of temperature, we look at the forward reaction. This enthalpy change is always representing forward reaction without it specifying, so represent from left to right. So here is negative, because these are lesser than 0 negative. That means it's an exothermic reaction. It releases heat. So when temperature increases, I'm just going one way, and then we'll try and think about whether this is the right way or not. If it is right, we get an answer. If it is wrong, it must be the opposite. When temperature increases, what would the system tries to do? The system, according to the principle, will try to decrease temperature, but your system only knows how to release heat. To decrease temperature means I must release less heat, okay? Therefore, system opposes the change. System tries to decrease temperature. How does it do that? By releasing, because all you know is release heat, but you release less heat. That is how you can try and decrease temperature. You release heat going from left to right. When you release less heat, you're going to favor backward reactions. When you favor backward reaction, you're going to get lesser N2O4. Therefore, the yield of N2O4 will decrease as the temperature increases. You want a higher yield of N2O4, so you don't want temperature to increase, you want temperature to decrease there. That's the only way you can go the other way, which is to favor the full reaction, and N2O4 will increase in the yield. So option B must be our answer there. Question 9, so we have some partial pressure of HI. This is 28 times the partial pressure of H2 at equilibrium. What do we have here? So if we have equilibrium partial pressure, I guess. So this is partial pressure. So if we have let the partial pressure of H2 be X, so this is X, then this will be 28 times X, because according to this information, not according to the mole ratio, according to the information, the partial pressure of HI is 28 times the partial pressure of H2, so 28X, not based on the mole ratio. That one will come later on. Now, if you have 1 mole of H2, you'll have 1 mole of I2. If you have partial pressure of H2 being X, you will also have the partial pressure of I2 being X as well. Because you started from HI, you didn't have any of these. When you generate 1 mole of these, you generate 1 mole of that. When you generate X mole of these, you generate X mole of that. And therefore, in terms of mole fraction, in terms of partial pressure, they're going to be equal due to the 1:1 ratio. Now, I can set up my Kp. Partial pressure of H2 to the power of 1, because there's 1 in front of the balance equation. Partial pressure of I2 to the power of 1. Partial pressure of Hi to the power of 2 square, because you have 2 in front of the balance equation. Now I'm going to put in the X, and the X, the one on top is from the product side, the one at the bottom is from the reactant side. Make sure you only put the square when you have the whole thing in bracket. You're going to get X squared over 28 square, X square, X square, X square cancel. I'm going to get 1 over 28 square. So I guess this answer will be very small. I can already see the answer is going to be A, but let me just check my calculator. It is indeed A. 1.276 times 10 to the minus 3. You get it to 3 significant, and there should be 6, which is bigger than 5. That goes up to 1.28 times 10 to the minus 3 there. Question 10, you have photochromic glass used for sunglasses, so they get darker when exposed to bright light. and more transparent when the light is less bright. The darkness of the glass, how dark does it get, depends on how much silver atoms do you have. So which statement about these reactions is correct? Cu plus and Cu2 plus ions act as catalysts. We know catalysts get regenerated, so catalyst is not used up. Catalyst is never used up. I can see the copper plus is there, and it goes via copper 2 plus, and the copper 2 plus goes back to copper plus. So I can see they're involved in this catalytic loop where the copper plus interconvert to copper 2 plus and get back to copper plus there. So in a way, they have already catalyzed the formation of these, they're catalyzing this process, I guess. But let's see what is going on for the rest of the statement first. Copper plus ions act as oxidizing agent. In terms of the definition of oxidizing agent, it oxidizes other substances, and what happened to itself? Itself will get reduced. So we look for what happened to the copper plus. The copper plus here is copper plus 1 because follow the charge of the ion, there's the oxidation number. Copper 2 plus, the oxidation number is plus 2 there. This is the increase in the oxidation number. So it acts as an oxidizing agent, itself should get reduced, itself should have a decrease in oxidation number. But we see an increase in oxidation number, so the copper plus is not oxidizing agent, it's actually a reducing agent. Number C, option C, reaction 3 increases the darkness of the glass. It says increases the darkness. So the darkness of the glass relates to the concentration of silver atom. So obviously the more silver atom you have, the darker it will get because silver itself is metal. Metals are opaque, so you can't see through the metal. So metals are opaque. And when you have reaction 3, you are reacting the Ag. So lesser Ag atoms should become more and more transparent, not become less transparent. This one say it increased the darkness, which is wrong there. Now the very last one, silver atoms are reduced in reaction 3. We have silver atom, silver 0 as an element, silver plus 1. This is an increase in oxidation number. So this is an oxidation reaction. So silver atoms are actually oxidized in reaction 3 and not reduced there. So leaving me back to my hunch, which indicated that A was the best answer after all.